Topic 1, Basic Skills. And 1.1 is just about models. And a model is an intellectual construct that helps us think about how a natural phenomenon works. Or helps us understand how a natural phenomenon works. So they're useful for describing various things that happen in the natural world, like the planets going around the sun, for example, or like the structure of an atom with a nucleus and protons and neutrons and electrons. But they can also be somewhat dangerous because just being a model, a construct of what is actually happening, at some point they begin to break down. So scientists have to continually revise their models. And so today we'll talk about two ways of making models. Okay? The first way is simplification. And simplification is just what it sounds like. Stripping a problem down to its basic components. Understanding is gained with those simple components. We're using the simple components. The more things are added, more more items are added until more understanding is acquired. For example, you might start out when we talked about with the planets, and you might pick a planet. And you might have the star or the sun. We know this planet is moving around the sun. We might look at the gravitational force, be interested in the gravitational force between the planet and the sun. To understand that gravitational force, we would look at things, we would need to know its mass and stuff. But we might make some assumptions, some simplifications, like perfect ellipse. No moon. homogeneous spheres. Where we know the Earth, for example, is a planet that is not homogeneous, as all planets are not, and neither is the Sun. And so, but to gain an understanding of how they would work and how their orbits would look, we simplify the process. And as more and more, if we want to gain more, well, maybe we add in a moon or something. So we put in the addition to the process of a moon. So of going around, we would also have the moon going around the planet. And that adds forces, new forces among the moon and the planet, and new forces among the moon, planet, sun system. And of course, if we go just to look here, there's an article in the National Geographic of August 2013, where here's a structure of a sun with planets, our solar system, and moons, a typical brass thing, and you see the person turning it here. And this is a model of our solar system. But the process of formation of the solar system has changed over time. And the way that our understanding of it is gained over time. So our model of the solar system is not today what it was back when these were being constructed, in the 1600s or even later. So, but like today, there's a picture, this loads, maybe. Go click on that from over here. There we go. It's where we see there's our solar system, but there may be large, giant other structures out in the cloud around it. So in this cloud structure here, it's called the Oort cloud. Orbit suggests the cloud seen here in cross-section is a spherical shell close to a light year across. And our solar system would be this little red dot in the middle, but out here is a bunch of parts that got there. And that the actual solar system's evolution to where it was involved its shifting, involved collisions of planets. And the title of this article is "It All Began in Chaos." So, but we got better understanding about the solar system as more information came in from meteorites and analyzing those and positions of the planets, if they are, and explanations for them. But it's still just a model of how our solar system formed and how it works right now with the limited information that we have. So that's a simplification. Okay. The other type we'll talk about today is an analogy. So we did simplification. We'll also do analogy. So this is when we know something about one process. For example, we'll talk about gravity and the electrical force. And we can compare or make an analogous comparison between the two. So in analogy, we compare a new problem to aspects of a previous problem. That we already understand. So for example, now we don't know this yet, but it's something that we're going to do in this course is get at the force of gravity, which is F, G, as a gravitational force, just like from dropping objects, things like that, and you see them go down towards Earth. That's gravity, of course. But in this class, we're going to define this mathematically, and it will be big G, which is a constant, times the mass of one object times the mass of the other objects divided by the distance between the objects squared. That's our gravitational force, and we're going to come up with that formula and construct it. But then later in the course, later in the year, of course you don't have to understand that formula right now, so we haven't done anything with it. But later in the year, we're going to see that there's another inverse squared relationship with electrical force. So you can see here as the two masses get farther apart, this D here, that their force between them gets much less in a squared ratio because you're dividing by a large number. The same thing happens with the electrical force, which is Fe, and that is constant K times the charge of one item times the charge of the second item divided by the distance between them squared. Again, it's an inverse squared relationship. And we'll also look at this. We're going to do a demo shortly involving light intensity that also follows an inverse squared relationship. There's differences, though, among these as well. The gravitational one here, this is all an attractive force, meaning towards each other. But the electrical force can be either attractive or repulsive, depending on the charges. And this one's based on charges, and this one, or the electrical force is based on charges, and the gravitational force one is based on mass. So those are just two ways of constructing and making models, and we'll do one of those in class. Now how about mathematical models? 1.1a, mathematical models. Now these are the powerful models for physics because, and this really brings up a close tie between mathematics and physics. In physics there's a lot of theory and models are constructed, but to really gain a lot of understanding of a process, we need to incorporate mathematics into the solving of physics problems in describing how nature works. So in this description of how nature works, okay, we would try to collect some data. And then we look for patterns in the data. And then we try to explain the patterns with mathematical models. And they can also, you can use the mathematics not only to explain the patterns, but also to gain insight into other parts or other parts of the problem. So this is allowing us to we collect some data. We'll do a lot of that in this class. We look for patterns in the data, and we explain these patterns with mathematical models. But then once we get the mathematical models, it might be able to use these to gain insight more into the problem, which makes it very powerful in physics. So, for example, well, if you collect some data, we'll just make it sort of non-specific data, but say you collected something on the number of missiles or nuclear warheads in communist countries. Those have fallen. We notice as the number of communist countries have went down, the nuclear warheads have decreased as well. So a small number of communists needs a small number of that. So we collect some data, and over the years we've seen the number of countries, and we could predict then, or we could interpolate in here with a linear function to explain the data of number of communist countries versus number of nuclear warheads. And if you wanted to know what would happen if, say, the number of communist countries decreased even more, we could look into this area in here, and that would be more of an interpolation, using our model to interpolate. So we don't have any data down there, but we can use our model to interpolate. We could do the same as the number of communist countries increase. We might use it to look out here in this region, because this model will extend out there, and that could give us an idea of, if we increase the amount of communist countries, the number of nuclear warheads would also go up, so how many would it be? Now there's danger in this, because if we got more data and we notice things like this, well then we're starting to think that actually the linear function doesn't explain the model perfectly either. So extrapolation can be dangerous as well. But sometimes, or many times, we do this to get at understanding, at least partial understanding or a good guess on what's going on out there. So let's look at some of these elementary functions in here and talk a bit more about linear functions, etc. Linear functions. So linear functions are the easiest ones to recognize because they're straight, right? Straight lines. Simple functions. And nicely, they come up a lot. In physics. Okay? So a lot of what we look at is explained by linear functions. And you have all seen this at some point, but the general form, for reminders of linear functions, was y equals mx plus b. But for us, many times the x and the y aren't x's and y's. Those are just symbols, but we'll use things like velocity and time and stuff like that. So we'll have different symbols, but they'll still follow, many of them, linear trends. So what is m? Well, m here is the slope. Y and x are variables, but b is the y-intercept, where our function, our line, crosses the y-axis. You remember on a simple y-x axis. Okay, we could have a line. A line might have a slope, and it might have, well, it would have a slope and a y-intercept to it, where it crosses the y-axis. So we could look at functions. Let's draw some functions now. I want you to try this along as we're working on it, okay? So draw a function. Oops, it's way too big. What we use all for? No, we won't. So let's draw a function where, assuming positive m, positive slope, going uphill. Let's look at when b is equal to 0. So try that. Good. So hopefully you drew something that looked like this. A line. B is 0. It crosses the y-axis at the origin. How about positive m still, but b is positive? That's right, is positive. Try that. Good. Hopefully you drew something that looks similar to that, where the b crosses the y-axis in the positive area. And then we could also do positive m. B is negative. Try that. Good. You get the hang of it. B is negative there. All right, let's do another one. Assuming positive b, so assuming a positive y-intercept, let's look at when the slope is 0. Try that one. Good. Hopefully you drew something like that. It would have the positive b and a 0 slope, flat. Okay, let's do positive b, and m is positive. Try that one. Good. Hopefully you drew something like this. Positive b and a positive slope going uphill. How about the last one, which I'm sure you could guess, positive b, whoops, and m is negative. Each of these will describe a different situation. Okay, good. That has a positive b, and the slope is going downhill. It's negative. So there's a big difference between if your data shows a trend with a positive b and where m is positive, or a positive b and m is negative. You know, there's different types of correlation. One means that as one increases, the other increases. But when m is negative, that means as one increases, the independent variable decreases. So it goes down here. So, okay, let's look at some data to draw these. And so let's do that. All right, so here's an example. So we'll just use standard data. It's just imaginary. We'll just do X's and Y's. So you collected some of this imaginary data, and you found for these values of X on your dependent variables. Do that right? Or you get values of Y of 11, 19, 31, 39, and 48. So to plot this data and analyze it, the first step is to look at appropriate scales for each axis. And we do this to maximize the area of the graph we use. We don't want it all shoved into one small little corner. 2, we plot the points carefully. 3, we use a ruler, best if it's transparent, because then you can see the data, to draw the best fit line through the data. It's not connect the dots. You're drawing a line through the data that gets as close to as many data points as possible. Of course, what we do with this math is actually you can solve for that mathematically what the best line is. And there's a method to do that. Many computer systems do it now. You can do it right on Excel. You can get your best fit line, and I'm sure some of you have done that. So, but then the next thing is to calculate the slope. I'll give you the formula in a bit. From 2 points on the line. And this is a big area where people make mistakes because they don't use points on the line, they use points from their data. Well, not all the data falls on the line. It bounces around. The line is a best fit through that. And then 5 is to write the equation of the line. Okay, so if we do that, let's plot our data. So let's first get some axes on here. If I put that on, what happens? Okay, that works. Shifts us, but this will be better. So let's say that our axes go from up here in the Y. We're dealing with all positive data, so I'm going to keep something like that. And our X went to there. So we can see that if we get our appropriate scale, X goes from 0 to 12. So we have the difference, it's 12 minus 0 is 12. And we have we count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you could do 16 divided by 12, but the best thing here I would think would be just about 1. So I'm not going to write 1, 2. I'm just going to skip the 1 and write 2 here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. And now that uses a good portion of my x-axis. When I look at y, I go from 48 to 11. Well, 48 minus 11 is 37. So I got to go at least 37. If I count the y's here, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, 48 divided by 12, I like to include 0 in there too. So if I did the whole 48 divided by 12, I can see that that right off is 4. So if each one of these was 4, that should work out pretty well. So 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, and that should get all our data in. And now I'm ready to do step number 2, which is plot the points carefully. My first point is 0. X is 0. Y is 11. 0, 11. Well, this would be right about there. And then my next point is 319. 319 would be about here. And the next point is 631. So that would be about here. And then the next point after that is 939. So that would come out about here. And then 1248 would be right there. And then the next step after I have this plotted, you can see it's found some sort of straight line close to it. We can use a transparent ruler to get those solved. So where's my ruler? Here it is. Okay. I have a transparent ruler that I can see through, sort of. I'm going to reduce the transparency on this a bit, make it a little bit less, like that, so I can see through it a little better. Make it a little bit more, sorry, maybe about there. And then I would take my ruler and get it so that most of the data falls through. A challenge to do on the smartboard, a little bit easier by hand. But anyways, so I can get an idea of maybe of how it goes through. That looks pretty close. And now I'm going to draw the best fit line on the edge of the ruler through this data. And I'll get rid of my ruler. And I have this line that fits the data. Now notice that it wasn't connected dots. Not every point. You get some of these aren't falling right on the line, right? You see most of them or all of them are off the line, except maybe the first one might be right on it. So then we're going to pick 2 points to calculate the slope. Now, I'm pretty sure all of you have calculated the slopes before, but anyways, I'm going to do it anyways. And if I pick at like at 2 and I go up from 2, I could see where it crosses, and I have a point there. And that point is approximately 2. Not quite 17, so maybe 16.8. That's my guess. I mean, I know it's close to 17, not quite 17 from what I have drawn. And then I'll pick another point, say at 10. We'll go up from 10. Go over. And here I have the point 10, 42, 40, 43.5, is my guess with that. The last digit there is an estimate. The 0.5 is an estimate. The 0.8 is an estimate. Now, the slope formula, if you remember, is change in y over change in x, or y2 minus y1 over x2 minus x1. The rise over run thing, where you take the y's and find the difference. So we're going to have this part right here. Let me get highlighted. Oh boy. This part is our change in y. Right there. And this, so we're going to do 43.5 minus 63.8. And this part here is our change in x, so that's going to be 10 minus 2. Okay. So, our y2 was 43.5. Our y1 was 16.8. Our x2 was 10. Our x1 was 2. So let's calculate that now. 43.5 minus 16.8 gives us 26.7. 10 minus 2 gives us 8. 20.67 divided by 8 is 3.34 is our slope. So this is our slope, m. Now the y-intercept we can read off, and it looks like it's going right through the data point of 0, 11. So 11 would be the y-intercept. So we have a b equals 11. So our formula for this that we calculated would be y equals 3.34 x plus 11. And then from that we could do things to calculate, like if say we wanted to extrapolate. So we could now extrapolate using our formula. For example, if we wanted to go out and look at what it would be out at, say, an x value of 20. So we would be going out, use a different color, out into this range, extrapolation. We could extrapolate to x equals 20. And if we did that, we would use our model to look at it. And we would get a y value of 3.34 times 20 plus 11 is 77.8. Outside our data range extrapolation. Okay, now But of course we need some units for these. We're just talking about x and y, but in physics we're always going to have units. We're going to have things that describe our numbers, that tell us something about it. For example, driving down the road at 50. 50 what? 50 feet per second? 50 meters per second? 50 furlongs in a fortnight? What is it? Or is it 50 miles per hour? Miles over hours. So it means you do 50 miles in an hour. Those are units for that. So in units, tell us the meaning of the terms in our models. So for mathematical models, we need units. And units give us the meaning of numbers in our models. Okay? We have to follow things that make sense. For example, you can say this for adding things. You can say it is true that 10 apples equals 8 apples plus 2 apples. But 10 apples is not equal to 8 apples plus 2 kiwi fruits. So you can't just add unlike terms, right? The apples, the units are different. They can't just be, you have to add like units. They cannot be different. So look at this example, okay? D equals 0.01, okay? And we're wondering what the units are for that. Times P plus 0.05. What are the units? N plus 0.25. What are the units? Q. Well, this is a common formula that would give us this something that we use every day. Give it some thought. Good. You probably figured out it was dollars, right? The number of dollars given the number of pennies, nickels, and quarters you have. So D, P, N, and Q are variables. Okay? Variables. 0.01, 0.05, 0.25 are numbers or constants in this. Now, every term, and to be able to add this and make this equation work, each of these terms, 0.01 with the units times P, 0.0 is one term, 0.05 times with the units times N is another term, 0.25 times the units times Q is still another term. And they have units associated with these numbers, 0.01, 0.05, 0.25. Those units have to give us, we have to end up with dollars to be able to add it, okay? So 0.01 is the value of a penny in relation to a dollar, isn't it? Okay? And if you had 5 pennies, you'd have 5 times 0.01 or 0.05 parts of a dollar. So the units, so that they cancel, have to be dollars over pennies. Because then the pennies, the number of pennies you put in on this side would cancel out, and you'd be left with dollars. So each term, the units are dollars. And we know over here we have dollars. Okay? On this one, it would be the same except dollars over nickels, and then quarters over nickels. But once you put in your number of nickels, you're left with dollars. And once you put in the number of quarters, you're left with dollars. So as an example, say you had 55 pennies, 2 quarters, 3 nickels, okay, how many dollars do you have? I just left out dimes so it wasn't confusing with dollars. So let's plug that into our formula. Well, D equals, actually let me just, plug it into the formula. D equals 0.01 D over P. That's out in front of the number of pennies. Well, how many pennies do I have? 55 P for pennies, plus 0.05 N over P. How many nickels do I have? 3N, plus 0.25 Q over P. How many quarters do I have? 3Q. Oops, I'm sorry. I messed that up a little bit. I got to go back over here. Thinking about nickels is on the bottom. I have dollars on the top. Hopefully you were following along. See the mistake there. And over here would be quarters on the bottom and dollars. So each term is going to give you dollars. And so you could see as you multiply this 0.01 times 55, the p's will cancel and you'll be left with dollars. So 0.01 times 55 is 0.55, but the p's cancel, D. And then we come to the next term. 0.05 times 3 is 0.15 N. And then the next term is 0.25 times 3, or 0.75. The Q's cancel, D. This is supposed to be D here. I'm sorry. Fighting. Okay, so 0.55 plus 0.15 plus 0.75 is $1.45. So the number of dollars is 1.45 D for dollars. So another example you might see is with temperature, going from Celsius to Fahrenheit, where the temperature you might have is the Fahrenheit temperature equals 5/9 the Celsius temperature plus 32. But each of these terms need units. This 5/9 needs a unit and 32 needs a unit. What we want is to get Fahrenheit for each term. So therefore, it must be written more correctly, TF equals 5/9, and the units on that, since we're going to be plugging in Celsius, would have to be degrees Celsius on the bottom, degrees Fahrenheit on top. That's our thing, times the TC. And on the 32, well, we need Fahrenheit. We're not plugging anything in next to it, so it would be 32 degrees Fahrenheit. So now you could see if you plug in, for example, what is the Fahrenheit temperature for 13 degrees Celsius? You could use your formula, TF equals 5/9 degrees Fahrenheit over degrees Celsius times 13 degrees Celsius plus 32 degrees Fahrenheit. And the degrees Celsius would cancel. You'd have 5 times 13 divided by 9, which is 7.22 degrees Fahrenheit plus 32 degrees Fahrenheit now to give you 39.22 degrees Fahrenheit is our Fahrenheit temperature. That doesn't seem right to me. 13 degrees Celsius, not 39. I think this is supposed to be 9/5. I have it written down wrong. Sorry. You gotta have your constant right. So that would be like flipping when I'm calculating the slope or something. If I flip the y and the x, it would lead to that mistake. So this is actually 9/5 times 13. So 9 times 13 divided by 5. So this should be 23.4 degrees Fahrenheit. And then when you add 23.4 plus 32, you get 55.4 degrees Fahrenheit. So you could check that. You can go to Google, right? Let's see. Oops. If you go to Google, or some other version and do Celsius to Fahrenheit, you could put in degrees Celsius at 13, and you'd get 55.4 degrees Fahrenheit. That makes much more sense than 39.2. But that also it's a good thing that actually that occurred, because it shows that, I mean, I know something about degrees Celsius and degrees Fahrenheit. 32 degrees Fahrenheit, 0 degrees Celsius. And I know the Celsius scale doesn't go up as quick as the Fahrenheit scale, so it didn't make sense that 13 degrees Celsius came out 39, because that's only 7 degrees above 32 degrees Fahrenheit. So knowing that, I could look at it and say, did my answer make sense? No, it didn't actually. So I could figure out what I did wrong. Okay, so that was 1.1. Next is 1.2, measured quantities, but that ends this video.